Now, what I am going to do is that I am going to discuss what is called the Feynman propagator, right? And this Feynman propagator is defined as the delta f. This f subscript is used for the to indicate that this is a Feynman propagator, and that Feynman propagator is x minus y is a 2-point correlation functions phi x and phi y, right? The phi x and phi y is vacuum expectation value in the time order product. This t is the time order operator. What it does is that this t operate on phi x phi y. It will give you phi x phi y if x naught is greater than y naught, and x naught, you know, is the temporal component of the 4 vector x, and y naught is the temporal component of y. So basically this is time. So this is that is why it is called the time ordering. If the time x t is more than y, then time ordering operator, when you operate, the earlier time will come first, and then the larger time will come first, and then the later one. But if y naught is greater than x naught, then this time ordering will give you a product phi y phi x. Just the order will be reversed, right? Now, you know, df, this Feynman propagator x is given by d. Then I can write this. This is actually the amplitude we have already calculated, y to x, right? So this is dy minus x if x naught is greater than y naught, right? And it will be dy minus x if y naught is greater than x naught. That we have already calculated. And then what we are going to do is that we are going to evaluate these integrations. This Feynman propagator for with argument x minus y is given by d4 integrations. D4 integration is d cube p integrations into dp0, where p0 is the temporal component of the momentum vector. So d4p divided by 2 pi 4 times this particular quantity I divided by p square minus m square plus I epsilon, right? I'll tell you what role this I epsilon plays and why we have written in this fashion, times e to the minus I p dot x minus y, where this p dot x minus y is again a 4 vector product. It will have p0 x minus y0 minus p3 vector minus x minus y3 vector. So this is the Feynman propagator as it is defined. You can also say that if f x minus y is the Feynman propagator in coordinate space, then I by p square minus m square plus I epsilon is nothing but the Feynman propagator in the momentum space. I by p square minus m square plus I epsilon is the Feynman propagator in the momentum space, because gf x minus y here is nothing but the 4-dimensional Fourier transform of this particular quantity. So df x minus y, if it is a propagator, if we have defined it as a propagator in the space, then I by p square minus m square plus I epsilon, this is the propagator in the momentum space. And this momentum space propagator, you will see, we'll be using in our calculations for, you know, Feynman diagram. So this is a very important component which we are going to build, which, that is the perturbation theory for this field theoretic calculation. So this is the momentum space operator, right? Now we will show you that this df x minus y is simply dx minus y if x not greater than y naught, and it is y minus x if y not greater than x naught. And dx minus y and dy minus x, this particular quantity we have already evaluated. Now let us evaluate these integrations. Okay, let us do that. So df is, you know, the delta f, the Feynman propagator, is d4p by 2 pi 4. This is I by this particular quantity. As I said, this is the Feynman propagator in the momentum space, and this is the e to the minus ip dot x minus y factor. Now I want to do this integration, right? Now, as I said, this integration I can do, this d4p I can write it d cube p into dp0 divided by 2 pi to the 4. I want to do this dp0 integration first, as indicated in the bottom of this page. Let us see how we can do this integration. This p square minus m square plus I epsilon, I can write this p square, this is a 4 vector. I can write this as a temporal p0 square minus p3 vector square minus m square plus I epsilon, where this p4 vector is nothing but p0 and p3 vector. P0 is the temporal component, and then p0 square is, I can write p square plus m square is ep square, that is the energy of the particle, p0 square minus ep square plus I epsilon. you note here, I am never saying that P0 equal to EP. The temporal component of this 4 momentum is not equal to energy. If that becomes, that is the pole actually. So P0 P0 square minus EP square is basically plus I epsilon written in this way. So P0 equal to plus minus EP is actually the pole of the propagator. Or you can also, let me make a comment here that P square minus this moment, if this is the momentum space propagator, then this has a pole at 4 momentum square, P square equal to M square. If you identify this M as a mass, then you can say define mass in quantum field theory like it is the pole of the propagator. Pole of the propagator is the mass of the particle. But then this is, we are talking about the bare mass and all that will come in the due course. What is the renormalized or physical mass will come later. Right now, so this D4P integration I have written in terms of 3 integral times this dP0 integration, and then I equal to P0 square minus EP square plus I epsilon. Now this function, this integration, this dP0 integration, I will do by using the technique of contour, by using the contour integration method, right? That we all know, from mathematical physics course. And similar kind of exercise I am going to do, you have done similar kind of exercise when you have solved the Maxwell equations. When you have calculated the Green's function for the Maxwell equations in your classical electrodynamic course. This is parallel to that. Okay. Now, where are the poles? P0 square equal to EP square minus I epsilon. Those are the pole. Then P0 equal to plus minus EP. I am taking the square root to find out the poles of P0. This is given by this. And this P0 I can write in terms of plus minus EP minus plus, because of this sign, it is minus plus I epsilon by 2 EP. I epsilon is a quantity which is very small. It's tending to 0, right? So this, again, I redefine this small quantity as again epsilon, or if you like, you can call it epsilon prime or delta. It is up to you. So at P0 equal to plus minus EP minus plus I epsilon, this is the where we have the pole. So suppose you have the plane P0, real P0 at this side, you put the imaginary P0, then P0 equal to plus EP, right, minus I epsilon, you have a pole. Other pole is P0 equal to minus EP and plus I epsilon here. So we have 2 poles. One is just in the below the positive real axis, and the other one is just above the negative real axis, right? So these are the 2 poles. Now I want to do this integration, by using the contour integration method. This integration, if I do by the contour integration method, you all know, then what I have to do, I have to first identify a contour and see what are the poles included within that contour. I have to calculate the residues at those for those poles, and then the value of the integrations will be the 2 pi I times the sum of the residues. If you have more than one pole, then you have to take the sum of all the residues. If you have a single pole, then it should be just the 2 pi I times the residue will give you the value of the integrations. So this dP0 integration, let us do. So I am just considering this d cube p, 2 pi cube, this is remaining. The dP0 by 2 pi, I by P0 square minus EP square plus I epsilon times this e to the I P0 times x0 minus y0 into e to the I P vector dot x minus y vector. Because what is appearing here, this e to the I P dot x minus y, this is a 4 vector product. So you'll have P0 times x0 minus y0 minus, and then this minus will make it plus p vector times what is that, p vector times e to p vector dot x minus y 3 vector. That is the integration. So let us consider only this this term which is within this curly bracket. Okay, so this part is this, that is what I want to do. Now how do I choose the contour? That is one issue what I have to keep in mind. So first let us consider that x0 is greater than y0, right? X0 is greater than y0. So if x0 is greater than y0, then x0 minus y0 is a positive quantity, I have to remember. Now let us see what is this value in the upper half plane. In the upper half plane, I can write the P0 as real P0 plus I imaginary P0. Like if you are associated with Z equal to x plus I y, so this is like x, the real part, plus I times the imaginary part. Okay. So this is this plus comes because I am considering the quantity in the upper half Z plane times x naught minus y naught. So this P0 I have just replaced by it. This is I am treating this as a complex quantity, though it is real, but I am treating it is a complex quantity because the integration which I am doing is along this real axis, P0 minus P0 equal to minus infinity to plus infinity. So the integration I am doing from along the real axis. But since I am using the contour integration method, I have to get a closed contour. Now, by taking into this real axis, how do I get a closed contour? That is what I am discussing here. And this exercise you have done in classical electrodynamics in the when you calculated the, as I said, the Green's function for the Maxwell equations. Okay, right now. So if it is in the upper half plane, then if you just calculate it, you will get this term imaginary P0 x naught minus y naught. And this quantity is always positive, right? Imaginary P naught in I am the upper half plane, x naught, I have taken x naught greater than y naught, then this is a positive quantity. So if I take the contour far away, right, this integral, this quantity will diverge. But what I want actually, I want the integration that should only survive along the real axis. So in the integrand must vanish in the other part of the contour. If I take the contour in the upper half plane, that is not happening. So I should not close the contour in the upper half plane like this. What I should do, I should actually take the contour in the lower half plane. Let us see whether I am correct or not. This same quantity, when I take in the lower half plane, then it is real P0 minus I imaginary times P0 times x naught minus y naught. This is this negative sign is coming because my complex variable Z is x minus iy. I am in the lower half plane. If I am in the lower half plane, then this part is coming as this. Now this you have a I, so this is a oscillatory. This will not diverge, but this part now it is coming like it was diverging for x naught greater than y naught in the upper half plane, but in the lower half plane, I am getting it. If I choose close the contour, like I take the real axis where the integration should only survive, and I need to close the contour, so I close it in the lower half plane. Then I can see in the lower half plane along the contour, this marked by this red line, the integrand itself will vanish when I take the limit P naught tends to infinity. So that is my correct contour then. So for the case where x naught greater than y naught, my contour should be this, right? So then I have only a single pole. So I have to calculate the ratio in this single pole. Then this value of this integration will be 2 pi I times the value of the residue in this pole, right? So that is what is how to choose the contour, right? That is a very well-known exercise, and as I have been repeatedly saying, you have done it for solving the Maxwell equations. Okay, so lower half plane, I should choose the contour so that my integration only survives for the real P naught, and in this plane, right, the integrand itself will vanish. So I am in the right direction if I choose in the lower half plane. So that's very easy then. In the lower half plane, what I do? Lower half plane, my pole is at P0 equal to plus EP, slightly below this real axis because of the presence of that I epsilon term. So the pole, I can calculate the residue at that pole. I know how to calculate. It is a simple pole. So complex variable, you have studied and you know how to calculate the pole. And the pole is, residues, and that residue will be this. And if it's the residue, you have to keep a few things in mind, that dfx minus y dqp by 2 pi cube. This was already there, and we are evaluating the quantity within this curly bracket, which I have put again here. And you had this e to the I p 3 vector times x minus y 3 vector. So this curly bracket 2 pi I times this residue is 1 by 2 ep e to the minus ep x naught minus y naught. This is what is my actually the residue. Right now 2 pi I, you come in for 2 pi I times sum of the residue, and this I was already there in your this was I was already there. This I was already there, so that I is of course will survive. Right now everything is fine. Now I have put a negative sign. I have put a negative sign because your contour, you please note this contour is in the clockwise direction, right? In the clockwise direction. Whenever you will have a contour in the clockwise direction, you have to insert a negative sign. If it is in the anti-clockwise, then that negative sign is not required. I'll discuss that part also. So that negative sign comes here. So this is fine, and my integration is dqp 1 by 2 ep e to the minus I p dot x minus y. And this, you please note, this was nothing but my dy minus x. Of course, this p0, this product is now again a 4 vector product. This ep is appearing here. With this and this, I can again write down this as a 4 vector product. And this p, the temporal component of p0 is now ep, because that is the value of ep. That is the limit I have taken here. p0 tends to ep. So this is fine. Now let me consider the case where x naught is less than y naught. When you choose the contour, now what you have to do, you have to choose the contour in the upper half plane. Why? Because you can check that very easily. Because let us see what was happening when I chose the contour in the upper half plane. You see, this is in the upper half plane, and then what was appearing here, x naught minus y naught. Now I am considering the case y naught greater than x naught. So if y naught is greater than x naught, then again there will be a negative sign. But that is happening in the upper half plane. So for the case y naught greater than x naught, you have to take the contour in the upper half plane again, so that the integrand again will vanish in this upper half plane contour, and it will only remain finite along the real axis. So the integrand will vanish again there in the upper half limit. Then following the same procedure, you can again find out the pole residue at the pole p0 equal to minus ep plus I epsilon. You can find the pole again, and then again within the curly bracket, this dp0 integration you can perform. Right? What you will get here, you will get dqp by 2 pi cube. There is no negative sign. That is a positive sign, which contour is again in the anti-clockwise direction. And then I was already there, and this is the pole minus y naught. That was the value of the residues. So as it is written clearly, this is the value of the residue, and then you the dfx minus y you get in this particular fashion, and you can combine them. Here again you have to combine them, and what you can see is that I can again write down this ep x naught minus y naught, and then you have 3 vector p 3 vector into x minus y 3 vector. So this is the spatial component of the 4 vector product, and this is the temporal component. I again combine them to make them a 4 vector product, where e to the I p dot x minus y, and p0 is evaluated at p0 equal to minus ap. And please note, this is nothing but the final for y naught greater than x naught. This is nothing but d function again, which says the probability of the particle which goes from x to y. Okay, so this is the Feynman propagator. Therefore the Feynman propagator in momentum space is I divided by p square minus m square plus I epsilon. This is my Feynman propagator. This we will be requiring when we will be calculating the real quantities like cross sections or decay rate and all that. When we calculate, and which we can compare with experiment, we will need this propagator. So this is fine. Now as I said, you can also calculate the Green's function of the Klein-Gordon equation. This is the Klein-Gordon equation. So this is del mu plus m square phi is equal to 0. So this is the Klein-Gordon equation. Now I want to find out the Green's function for this equation. And how do you define the Green's function of a differential equation? The Green's function is defined as the solution of the same differential equation when you replace the source by a unit source. So delta function is a unit source. So when I replace the unit source, in the Klein-Gordon equation, when I replace the 0 by this unit source, then its solution is the Green's function. That is the definition, standard definition of the Green's function, right? Now, this Green's function I want to find out. What I will do again, I'll solve this equation in momentum space. So what I'll do, I'll take the Fourier transform of this momentum of this equation. Now, Fourier transform of the Dirac delta function is always 1. That we know. If I take the 1 and its Fourier transform will be Dirac delta function. So inverse Fourier transform of this function, Dirac delta function, is 1. And let me consider the Fourier transform of this G Green's function as G tilde, which is a function of P. And this is the definition of the Green's Fourier transform. G x prime is d4p by 2 pi 4, because I am in 4th dimension, d cube p into dp0. So d cube p is the spatial component, dp0 is the temporal component, e to the minus I p dot x minus x prime times the G tilde p. This is the Fourier transform of G. Now, other day I have shown you, when you take, if Gp is a Fourier transform of G, then its derivative will have a Fourier transform minus ip times Gp. And if you have a double derivative, then that will be ip square times Gp. So if ip square is give you, I is the imaginary root of minus 1, square root minus 1. So square of that I will give you minus 1. So the del mu will be just, in Fourier space, will be just replaced by minus p square plus m square G tilde p. This is the Klein-Gordon equation in Fourier space for the Green's function G tilde p, and this is minus 1 because the Dirac delta function has a Fourier transform which is unity. Now you can see this Gp is nothing but is 1 by p square minus m square, right? Now you see this I times G tilde p is I by p square minus m square, which is the propagator, right? This Feynman propagator which which is the propagator which we have just calculated. You'll see these are just simply I by p square minus m square plus I epsilon, where this limit epsilon will be always taken to 0, right? Now, so for the free Green's function, for the free propagator is nothing but the Green's function for the Klein-Gordon equations. One more point let me try to emphasize here. You see this I epsilon, though this limit is tending to 0, this is shifting the pole either in the upper half plane or lower half plane. And that is actually, it's setting the boundary condition. See that epsilon is in some sense very powerful because it is setting the boundary condition. That is telling me whether I should, for x naught greater than y naught, I have to choose the contour appropriately, so that in the except the real axis, the integrand vanish in the other part of the contour, and which part of the which contour, which pole I should pick up, or at which pole I should need the residue, that is actually set by that I epsilon term. So that is the comment I would like to make here. And the Klein-Gordon equations, as I said, its Green's function is nothing but this. Okay, so this is what is the propagator. That's what I wanted to calculate, and this is very important in this sense, as I am saying repeatedly. This will require when we calculate the real quantities like the cross sections and decay rate of the particles. Now, so far what we have done, we have calculated only we have only considered the free field part, not introduced any interactions. But whenever, unless your system is interacting with anything, you cannot learn anything about that. So to learn about the system, we have to introduce some interaction to the theory. So far, the Lagrangian density for the scalar field, real scalar field or complex scalar field, whatever I have introduced, it was the free part. It was giving the free Klein-Gordon equations. Now, I want to introduce the interactions. And to introduce the interaction and to systematically develop the perturbation theory, I need to discuss the following things. Very, I'll go slowly. This part is very important. If you have any problem, just stop me. Okay. And to introduce this interaction, I need to discuss three pictures of quantum mechanics. One is Schrödinger, one is Heisenberg, another picture is Dirac picture. Sometimes this Dirac picture is also called interaction picture. So now I am going to introduce the interactions towards going the. I am going towards the calculation, real calculations of cross sections or something. Before that, of course, I will develop the Feynman diagrams technique. Okay. Now. The time evolution of any state psi s stands for Schrödinger, is governed by the following equation. You know that this is I ddt operates on this state psi s for Schrödinger is the total Hamiltonian H psi s t, right? And this normally what you see is that I h bar times ddt, but then h bar is taken as 1 in our calculations in our unit. And then if you take this is the Kate vector for the Bra vector, this will satisfy the equation minus I ddt, this Bra vector times psi s h dagger, right? But if h is a Hermitian operator, then h dagger will be equal to h. Now Hamiltonian h. Now in the Hamiltonian h, so far we have taken this Hamiltonian as a free Hamiltonian. Now I want to introduce the interaction. So this h I write as a sum of two terms. That's the Hamiltonian h is equal to h0, which is the free part of the Hamiltonian plus some interaction denoted by HINT, indicating that this is the interacting part of the Hamiltonian. Okay, that is what we are actually discussing here. Now, in Schrödinger's picture, this operators has no time dependence. So suppose omega is a operator in the Schrödinger picture denoted by s, omega s dot. By dot we mean time derivative, then that is 0. The operators are time independent in Schrödinger picture. Now, the solution of this equation, this particular equation, I ddt of psi s going to h equal to h psi s, can be written down formally as the psi Kate vector psi t is e to the minus I s t psi s at t equal to 0. Similarly, the solution of the other equations will be minus I ddt s is equal to psi s h dagger, which is psi s h, and which is given by psi s t psi s 0 e to the plus I h t, right? So these two solutions we have got, formal solutions we have got. Now we want to calculate this particular quantity. The expectation value of this operator omega s in the Schrödinger picture, right? Within this state psi s t, I want to calculate, I want to see how this evolves with time. So the derivative with respect to ddt. Now this ddt psi s omega s psi s, this particular quantity, I can see this. First you take derivative this two it keeps same, then you take this and take the derivative here, and then at last you will have the derivative over this, right? This is what is the normal differential rule we know. Now, what I can do now, you'll see this del psi d, this del psi del t, this is lost. Okay, this equation, this del psi, these are the two equations they satisfy. So what I can do there, that in this del psi del t, this when I have a derivative of this Kate vector, I can write this as minus I h times psi s, right? So here I will write minus I h times psi s, because the time derivative of this, I times time derivative of this is h psi, and I times this minus I times this time derivative of this is h times that. So this here what will appear when I write this as h into psi, you will have a h omega s, And when here I will write in terms of h, I will have omega sh. So this h omega s and omega sh will give me a commutator. So if I take the derivative, then those two terms will give me a commutator, right? So this is the commutator omega sh. And the other term, which has the simple derivative with respect to, which has the derivative of this operator omega s, that remains. I kept that intact. This is the other term. Okay. Now what I can do is that I want to take away the time, this time dependence from the state, right? So this psi s I can write, or let me say this psi s I can write as psi s t. This is a function of t as e to the minus I h t psi s 0. So essentially, what I am doing here then is that I am taking away the time dependence from the state side. Similarly here you have this. I can replace that as a psi 0, right, e to the IHT. So this psi which will appear here now will have argument 0. That means what I did here, I have taken away the time derivatives from the psi and put it in this way. Okay. And I do the same for this, so then this side I had the commutator. What I did here, I have again taken away the time derivative, time dependence from that psi. Time dependence from that I have taken away. From here also, where d omega s dt appears, I have again taken away the time derivative from this particular quantity, so I got this. Now this commutator will be e to the IHT omega s into h, right? Now what I can, so this is omega sh e to the IHT times e to the minus IHT. Here it is the e to the IHT, h omega s e to the minus IHT. What I do here, I had introduced here a unity 1 by introducing here e to the minus IHT e to the plus IHT. So this is I introduce here. Where I am doing this, please see that I have here e to the IHT omega s e to the minus IHT. So if I introduce here a e to the IHT omega s, and if I have a e to the minus IHT, then this and this quantity will be same, right? And then I will have e to the IHT here plus e to the IHT here, but h here I have h, in the exponential I have h, here in the exponential I have h, so h and h operators will commute, so they will get cancelled, right? Now here again I to have the time dependence of omega s, I again introduce e to the minus IHT times e to the IHT, which is again 1, right? Then I have again omega e to the IHT omega s e to the minus IHT, like this quantity, and again I have e to the minus IHT here. That minus IHT I can take this side because h and e to the IHT will commute, and then when I take this away, this IHT will combine with this minus IHT and I will get 1. Okay, so this trick if you do, then what you get this following expression, right? Now what I do, I define, so this omega s, the operators in the Schrodinger picture, I write that e to the IHT omega s to the minus IHT, right? I write this as omega h, the omega in the Heisenberg picture. Please note that yesterday I have used this particular relations to calculate the time dependence of the operator A, annihilation operator A. I had the annihilation operator which has AP at time t equal to 0, and when I wanted to calculate the AP at any time t, I had multiplied it by e to the IHT, and this side e to the minus IHT, expanded that for small this HT, and then I got that commutator, and that relations I have used. So this is today I am giving you the derivative how it comes. So once you do that, then you get ddt, this omega h has absorbed all this e to the IHT factor. All the IHT factor has been absorbed by e to the omega ht, and then if I just note that, then this equation is telling me ddt of omega h is equal to d omega h dt plus I times the commutator I omega h. So this is the famous Heisenberg equation which gives you the time evolutions of the quantum mechanical operators. So this is the famous Heisenberg picture. Please recall your classical mechanics. You have used similar kind of equations like dF dt is del F del T plus FH Poisson bracket. So this is exactly same. Only difference is that formally it is same. Only difference is that here you have I and it is no I. Of course, if you don't work in the natural unit, then of course some H bar will come in your quantum mechanical equations. So this is very parallel to the Poisson bracket equations of motions in classical mechanics which you use, and this is the Heisenberg equation, where we have defined this Heisenberg operator as e to the ist. H is the total Hamiltonian. You remember this is omega s e to the minus ist, where H is the total Hamiltonian. Now, so I know how the operators evolves in time. This is fine. But now, what you note here is that what is involved here is the total Hamiltonian. Now, for any physical process, we want to learn what is happening due to some interaction. We are most of the time not interactions about the free system, right? We are always interested when to learn physics when the system is interacting, right? Unless it is an interacting system, we cannot learn any physics out of it. So the time evolution here involves the total Hamiltonian. Now, what I want actually, I want to know through interaction how the system evolves, right? So suppose you are doing some experiment, let us say in some high energy experiment where two particles collides, right? Now you have the particles which will be coming from some source, maybe from the accelerator, and then you will have a target which it will hit, and then after the interactions of the projectile with the target, it will fly some distance, large distance, and hit your detector. You detect that particle and learn something from that. Now you can only learn something when the projectile is interacting with the target. If it does not interact, you will not learn anything, right? So then what we want, but one interesting thing you please remember. One interesting thing is that when the particle is coming from far away, right? It is like a free particle. It is like a free particle. Now it is coming and interacting with the target for some time. There is some interaction time for which it will interact. And after the interactions, it will again fly and go far away and hit a detector. So, and when it is detected again is a free particle, right? So when it is coming from the source, it is a free particle. When detected, is a free particle, but in between there is an interaction. If there is some interaction, then only we learn something, right? Now, so then what we need actually, we need a we need a picture where the states with free Hamiltonian, right, coming from the remote past as a free particle, as an eigenstate of H naught, because it is a free particle, interacts and then again detected again as a free particle, as a eigenstate of H naught. But in between there are some interactions, right? So I want to separate these two things. I want to wash out the H naught evolution due to the H naught part, because I want to learn something which is happening because of the interaction. So you see, so this thing I have written in detail that we would like to study the evolution of the system due to the interaction only. But the Heisenberg picture, you please note that it is a total Hamiltonian. It is not containing only the interaction part. It is containing the total part. I want to separate that out. So study the evolution of the system due to interaction only. We need to work in a picture which is called interaction picture or Dirac picture. So Schrödinger picture I have discussed, Heisenberg picture I have discussed, but I am arguing that I want the system, I want the signature of the interactions, and for that to learn some physics out of it. So to do that, it is always convenient to work in the Dirac or interaction picture, so that the time dependence due to free Hamiltonian is washed out, because H naught, the free part, will always give you some time dependence. It will give you the time evolutions of the state, right? So if a particle from the source directly goes and hits your detector without the interaction, you don't learn anything. So the free time dependence due to the free Hamiltonian part, I want to wash it out. And how can I do that? That can be done by using the Dirac picture, or what is called the interaction picture. So let me discuss what is interaction picture. Okay, this is extremely important, because you know this tells you how to develop the perturbation theory in the interaction picture. Okay, so now what I do, I define a interaction picture state psi with the subscript I as e to the I h naught t. Note there, I have not taken here the total Hamiltonian. I have taken only the free part of the Hamiltonian. My total Hamiltonian was h naught plus h in interaction. That I have taken here only h naught. But note that the h which appears in the Heisenberg picture is the total h. It contains both the free part and the interaction part. I want to wash out the interaction part, sorry, the free part, evolution to the free part. So what I defined the state psi I, right, it is the I h naught t operating on psi s, right? And this I, as I am saying, this indicates, this subscript indicates that you are in the interaction picture, and this picture is also called Dirac picture. So now what I do, I operate on this psi I operate this Hamiltonian I ddt. If you have you know this h bar, then you will call it h. So I just take the time derivative of this particular psi. I get here e to the I h naught. So this I is multiplied here. Now when I take the derivative, I get another I h naught times e to the I h naught psi s plus e to the I h naught. And you know the Schrodinger psi depends on time, right? So there the states are time dependent, but operators are time independent. So then I get I have a derivative, another term ddt of psi s. So time is, if you just subtract out one I from both sides, then what I am taking here is partial derivative of this both sides with respect to time, right? This I have put just so that I appear here, and I can write I ddt psi s as h psi. Okay, that was the whole purpose. So now I ddt of psi I equal to minus h naught e to the I h naught psi s e to the I h naught h psi s, right? Now I can write I ddt of psi I. This h naught I can take in the this side, because h naught and h naught will commute. So e to the I h naught t. Then I have h minus h naught operate on this psi I. Okay, psi I. There is a psi I here. It is very faint. Probably you have difficulties in seeing it. So now you see I have I ddt psi I e to the h naught t. H minus h naught is nothing but the interaction, right? So now I have the interaction here, right? Only the interaction Hamiltonian is coming here. That's what I want. I want to wash out the free part. So this I can write again I ddt. I is operating on psi I e to the I h naught, and this I int, because this h minus h naught is psi interaction. This is psi s. Now again I introduce a 1 here in the form of e to the minus h naught t times e to the plus h naught t, right? Now if I do that, then I have e to the I h naught t times h interaction e to the minus I h naught t. And see, this is my hi. See, this interaction picture evolved, this interaction Hamiltonian h evolved by the free Hamiltonian. So this is called Hamiltonian in the interaction picture hi. And this is nothing but again e to the h naught t psi s. That was my definition of psi I. So this, then I have I dt on this psi I is hi I. Please note one thing, that this the state psi I if contains the time evolution operator e to the h naught t. So free state, the eigenstate of h naught, you know, is there, and then you get this particular equation, and you see in this particular equation the total h, the h naught part is not there, right? So if I solve the equation, this only contains the interaction hi, right, e to the h naught t, and this is only simply the hi, the interaction Hamiltonian in the interaction picture, right? So let me just very clearly tell you here, if this H interaction is an operator, if it evolves by the total Hamiltonian, then I will call it a Heisenberg operator picture. If it is evolved through only the free Hamiltonian, then it is the Dirac picture, or we are calling it interaction picture. So this is the Heisenberg picture. But if only the free part is there, then that is called the interaction picture. And by doing this trick, please you go through this, because this is very important, and you see I have a differential equation like the Schrodinger equation again, but only what is involved here is the interaction. Okay, nothing else. So therefore, this hi is the interaction in Dirac picture or in the interaction picture. So I have written down this equation in the Dirac picture, where I have only the interactions. The total Hamiltonian the h naught part is not there, right? And that is what we want. We want to learn about the interactions, not interested how a free state will evolve from one time to another time, right? Therefore, now we you know, now, so what we got actually, we got this interaction picture, the evolution equation, we call it evolution equations in interaction picture, or the Dirac picture. So now this psi I, so let us define a psi I, psi in the interaction picture at time t, which how it suppose you have a psi in the interaction picture at time t0. I want to know how it evolves to time t. And let me define an operator. I assume there is an unitary operator ut t naught, which operates on this state at t naught and gives me this psi at t, right? So this is what we want. Please note that what I have done here in the entire exercise, I have washed out the presence of the free Hamiltonian by or through a unitary transformation. So through unitary transformation, I have washed out that particular part of the Hamiltonian. Now, what I want to learn is that how a state in the interaction picture or Dirac picture at time t naught evolves to a state at t, right? I am assuming that this evolves through an operator when an operator u t naught operates here, right? Now, taking a derivative of this equation, now we take a derivative of this equation with respect to t. So this is a derivative, and then this is a function of, you know, of time. So I have a du dt term and psi t naught, and other derivative doesn't exist because this doesn't contain any t dependence. So this is the equation which I get, right? Now this I ddt operates on this, the time evolution of this psi I t is nothing but hi, the time derivative, the partial derivative of this particular state, right? I ddt of psi I is nothing but hi psi I. That is what I have derived. So what I can do here, I can just replace this by hi psi I is equal to I du dt and this particular quantity at time t naught, right? Now this is how in the interaction picture how the evolution equations is now we have got. Now what we can do, we can write this psi, this is at time t. So this I can replace this psi it by this operator u and psi at t naught, right? This I can replace by this. Once you do that, why I'm doing that? Because in this side I have psi at t naught. Somehow if I can get a psi at t naught here, then I will be able to get a evolution operator for the u, time evolution operator for the time evolution equation for the u. So if I replace this psi by this particular quantity, I get, right, hi u psi at time t naught, I du dt psi at times t naught. That tells me that I du dt is nothing but hi u. So now what I've got, I have got an equation which tells me how the operator u, right, evolves with time. But what is involved here is nothing but only the interaction Hamiltonian. So this is very interesting in this sense, because you see this u is only involving the interactions, and as it is defined to the interaction, how a state evolves, that I will know, and that is what I want to know, how a state after interaction, how it evolves. That will help me to learn physics about the system, right? So this is the differential equation which I have got. I du dt is equal to hi u t t naught, right? This is the differential equation I got. And remember, this u is a unitary operator, and this equation now I need to solve, right? So this u, please remember, this tells me how the states evolve. That is what this u will tell me. Now, of course, when both the argument of this t of u is t naught, initially it should be 1, because that is the state, nothing to evolve. So this will be 1. So I have to solve this equation. I have to solve this equation with this initial condition. Okay, so I have to solve this equation. So this equation can be solved by using the method of iteration. This is a differential equation, and if you have studied the integral equations in your mathematics course, in your mathematical methods course, then this differential equation can be converted to an integral equation with the boundary condition built in, and that is what is done here. In a differential equation, you can convert to an integral equation. And in that integral equation, so the initial conditions or boundary conditions will be built in. That is what, and also it is, some of you have followed the book by Artkan. It is done in the at the last part of the book. It is done, right? So this is an integral equation, right? Now this differential equation, I convert. I just convert that to an integral equations. Why I am calling it a integral equations? Because when you call a differential equation, I will call an equation a differential equation if the unknown is under the differential sign, right? If the unknown is under the differential sign, then that is a differential equation. Now you see this u in this differential equation, I can write in this form, and let me check whether it is right or not. See, if t equal to t naught, this term will vanish, and at u t naught will be 1. So that's the boundary conditions or initial conditions satisfied. And this is the equation which I get. So this is the equation which I get, and this is an integral equation. This is an integral equation because the unknown u is there in the integral sign, right? So unknown is there in the integral sign, right? So as I said, the equation is a differential equation whose unknown is under the differential sign. So this is an integral equation because its unknown is under the integral sign. So this is the differential equation, and that there are several two types of the integral equations. One is called Feldholm, other is called Volterra. If the limits of the integrations are variable, then that is called Volterra differential equation. If the limits are constant, like numbers, then they are called the Feldholm equations. So this is a Volterra type equations because the limit is a variable. T is a Volterra type integral equation. I am saying that because if you have a mathematical background, then you can get the feelings of what is going on. And there are also the differential equation is divided into other two kinds. If the unknown is only involved in the under the integral sign, then it is called integral equation of first kind. But if the unknown is both outside and inside the integral sign, then it is called second kind, integral equation of second kind. So this is of course an integral equation of second kind, because unknowns are both there outside and inside the integral sign. And this is a Volterra integral equations, because the integration limit is variable. Okay, and there are standard techniques to solve this, but one should be little careful here, because we are not dealing with the simple functions. Both u and h, they are operators. So this is a very important thing to remember, that they are operators. So you should be careful, because operators will normally, they will not commute. So while solving that, you have to be careful. Now you can solve this equation by the method of iteration. So what is the method of iteration? So you know, the u t naught is equal to 1, right, times this. So first iteration will be just, I will put 1 in place of u. So first approximation of that equation will be u1 t naught equal to 1 minus I t naught to t u t prime t naught dt prime, right? So the first. Now what I should do in this was my differential equation, original differential equation. Again, I have written for you. What I do here, this is the first approximated solution. Now I will put here, right, in this place of u. Then what I'll do, I'll get this particular equation. And then in the third iteration, what I'll go, this whole thing I'll put again in this u, and go on doing this. If you go on doing this, then you will get the solution of this equation ut. And one can show that ultimately, if you go on doing that, then what we will get, you will get that u is equal to, you know, as you go on iterating, number of integration increases. From first it was only single integration, second integrations, then u t t naught, you will, if you go on, you will get this kind of solution for that differential equations, because this is the solution of the integral equation. But you see, what is involved, very interestingly, is only the interaction. So this is the evolution operator, which contains only the interaction part, right? Therefore, this is something which will help us to learn the physics due to the interactions in the system, which is very important. Now, you know, as I said, in any experiment, you know, when you do some, let us say, some scattering experiment, the beam comes from far away from the target. When the beam is leaving the source, it doesn't interact with the target. That is what is called far future. And after the interaction, it is detected in the detector, which is also far away from the interaction zone. So that is called the far future. And then the other one is that remote past. So so this u can help me to learn. So you know, the time here is that limit is there from t naught to t. Now if I take that t naught is equal to minus infinity, right, then I am in the remote past. And then if I take t tends to infinity of this u, I am in the far future, right? And then from remote past to far future, I am going through this interaction. So this u is the ideal quantity which will help me to understand the physics. And this u actually, in the t naught, initial time tends to minus infinity, where the particle was in the starting from the source, and then t tends to infinity, the far future, when it is detected in the detector. So this s, this u at this two limit, t naught to minus infinity, remote past, and t to plus infinity, far future, that will give me nothing but the scattering operator or the scattering matrix. So we are now got something which we have you know, familiar with, the scattering matrix we have got. Now if I know the scattering matrix for this interaction, then I will be able to calculate the cross section. But please wait, we have to develop the theory very systematically so that there will be no confusion. So you see the incident beam, which is coming from T0 to minus infinity, by that I mean remote past, interacting with the target, and after the interaction with the target for a short time, that particle again moves toward the detector and get detected at the detector at t tends to infinity. And this entire evolution I can study by taking this particular limit of this vector. So this is what we want to do here. So therefore, you have an initial state I, right, at t0 tends to minus infinity. And please note that t0 equal to minus infinity, the state which you have, that is a eigenstate of H0, because the particle was a free particle, so that must be the eigenstate of the free Hamiltonian, right? So this I is the eigenstate of the free Hamiltonian, right? Because it was in the remote past. After the integration, right, that again with the target, then it goes to the detector at the far future. Now, so this SI, this S, what contains the interaction, this is responsible for evolving the free state H0, free state H0, free state of the the state of the free Hamiltonian, this I, with this S contains the interaction, right? The S contains the interaction because U contains the interaction. So the free state I, by free state I mean the state of the free Hamiltonian, right, interacts, and that becomes a state SI. So with this, if I operate S on this, then I get the information about the interactions, and this actually goes and hits the detector. And in the detector again, it is a free particle. So if I take the projection of this SI with F, the final state which you have detected, and which is again a eigenstate of the free Hamiltonian, that matrix if SI is not from there I can calculate the cross section, which can be compared with the experiment, right? Which can be which can be compared with the experimental result. But wait, we have to do some more formalism before we call it a day. We have to systematically develop the Feynman diagram techniques and all that. So this is something which is we are going closer to the from the field theory towards observation. Okay. Now let me make a point here, is that this SFI tells me how the initial state I, which is a state of the free Hamiltonian, evolves due to interaction S and gets detected in the detector. So this contains the dynamics of the whole process. So because it contains the interactions, and for any physical process to happen, you need two things. One is the dynamics, and the other part is the kinematics, the phase space part. I'll discuss that later, maybe in some later day when I really calculate the observables. Now, please note here one important thing is that limit of when I have evaluated this U, the limit of this integration is from T1 to T, and then from here it will be T2 to some T3, and then last it is T0 to Tn minus 1, right? Now, what I am trying to say here is this integration limits are different. Now, but what we want actually, we want all the limits of this integration should be same, so that I will be able to take the limit T0 tends to minus infinity and T tends to plus infinity. I need for all the T integration, I want the same limit. For that, you have to do some algebra again. These are the very salient point of these calculations, but you have to know if you want to know the formalism well. Okay. So now, so please note that the integration limit is different from T0 to T1, T0 to T2, and T0 to Tn. So all the upper limits are different. What I want actually, I want all the lower and upper limits should be same. Okay. Therefore, I have to do that, so that if I do that, then I can go from remote t naught minus infinity, I am in the remote past, and t plus infinity, I am in the far future. If I don't have that, if the limits are different, then I have a problem. Now, let us see how to do that. See this, we begin with these indications. When I have these second iterations, right? And what is there? Where is that? This one. So this one, U2, I have two integration, t naught to t and t naught to t prime. And what is involved here is 2h, product of 2h. This is the second iteration. Okay. So let me see. So this, let me consider this. If I can do this for these double integrations, I should be able to do in principle for 3, 4, and all that. Okay. Now, so I have the integration between T1 and T2. This is very crucial. Probably it may be difficult for some of you, for the young students, to understand. But if you have any difficulties, please go through it and let me know later. So this T naught to so this is the T1 axis, let us say, and this is the T2 axis, right? And now you want to integrate this two-dimensional dt1 dt2 integrations for this interaction Hamiltonian HIT1 times HIT2. So what I do here to do these integrations, I just pick up a T1, right? I just pick up a value of T1 and do the integration over T2, right, from T0 to T1. Once I perform this integration, then everything becomes a function of T1. Then I vary T1 for the entire region. By doing that, what I am doing the integration along this particular triangle, right? So this particular triangle is actually half of this square, right? Now, this particular integration, again, this T1 and T2, they are dummy integrations. So I can just interchange T1 and T2. So this will become T2, this will become T1, this will become T2, this will be T1. Okay. So if I do that, because that is perfectly allowed, because there's a dummy variable, I can always change that. After I do the integrations, there will be no sign of that T2 and T1, because everything will come as a function of T0 and T. So once I reverse this integration, then I do the opposite thing. What I do, now I pick up a T2 and integrate over T1 from T0 to T2, and then again I vary T2 from T0 to T, so that if I do that, I will be doing the integrations in this half circle, in this triangle, which is again half of this square. So if you do this integration this way, then what we are getting, actually, we are getting the value of this integration as half of the integration over the whole square. But remember here one important thing is that I have HIT1, HIT2, right? And when I am saying I am making it, I am this dummy variable I am interchanging. This is HIT1, this is HIT2. I have to remember that HI is an operator. So this interchange, they may not always commute. So I have to be very careful. Please note that in the lower half, when I am in this triangle, then you should remember then T2 is less than T1. So when I am doing this, when I am doing this integration when I am doing, T2 is less than T1, and everything is written here. You must go through it. Board would have helped me, but that's the limitation we have to suffer anyway. And when I have in the upper half triangle, then I have T1 less than T2. So again, what I have to do, I have to introduce a time ordered operator here, because I have to see, this will contribute if T2 is less than T1, and this will contribute if T1 is less than T2. So this ordering, whether HIT1 will be fast or HIT2 will be fast, right, will depend among this time T1 and T2, which one is larger and which one is smaller. And that can be implemented by introducing a time ordering operator, which is also called chronological operator, by introducing a chronological operator. So just I put that chronological operator. So you have to check whether T1 is greater than T2 or T2 is less than T1. And then, as I said, this will be the half of this. Please go through this, and it is written in very detail, so it will be very interesting to, but it is very much required. Now, this T, is a time order product, time order operator, as I have told you. And if you go, this I have done for, so this, by doing that, the limit of the integration is from T0 to T, T0 to T. So now I can take the limit T0 to minus infinity, T2 to plus infinity. So it will be integration from minus infinity to plus infinity. That is what I want, because my source and the detector are far away from the interaction zone. And for the n such integrations, all the lower limit will be minus infinity, upper limit will be infinity. And this S will come as a time ordered product, as I indicated. Why the time ordered product? As HIT1, HIT2, and so on. Now, so this, suppose we consider the S2. If I to consider the S2, it will be 1 by factorial 2, DT1, DT2, only 2, and then time order product of HIT1, HIT2. Now, this H is a Hamiltonian, but we are working with Lagrangian density, Hamiltonian density. So this HI will be d cube x, the integration over the volume of this Hamiltonian density. Therefore, this S2 I should be able to write, already T integration is there, and d cube x will come. So there will be d4x integrations of this time order product, because always we write down the Lagrangian density for a continuous system, right? So this part is very important. I mean, I guess there may be some understanding problem in this part. So please see, otherwise tomorrow again I will explain this part, but this is crucial to important. And this kind of change of variable and integrations, if if probably in some other area of physics, in non-equilibrium statistical mechanics and all, you might have also encountered. Some of you might have encountered. Now the next question will be how to evaluate this time order product, right? You have the time order product of the operators. Now, in the scattering matrix, I have the time order product. So to calculate the scattering matrix, and from there, how to calculate the cross sections, draw the Feynman diagrams, and calculate the cross sections, we need to know actually how to evaluate the time order products. And to calculate the time order products, there is a famous theorem called weak theorem. Okay. Now, in this weak theorem, I will just introduce something which I will elaborate tomorrow. So let me just discuss something which is, you may think that it has nothing to do with the weak theorem, but tomorrow I'll show you this is very much relevant. So before I discuss this weak theorem, let me do an exercise that I do some Gaussian integrations. Okay, I have some time, so let me discuss this part. Consider a Gaussian integrations which you are doing from minus infinity to plus infinity dx e to the minus alpha x square by 2. The standard technique to do this integration is to square it, and you will see why I am squaring it. I square alpha, this times dx e to the minus alpha x square times dy e to the minus alpha y square by 2, because x and y are dummy variables. Okay, this I can write as integration over dx dy e to the minus alpha x square plus y square by 2. Now I change a variable from xy to r theta, this from Cartesian to polar coordinate, and then this dx dy will be dr d theta, r dr d theta. So I put here r dr d theta. Limit of r will be from 0 to infinity, and the limit of theta will be from 0 to 2 pi e to the minus alpha r square by 2, because x square plus y square is r square. And note that there is no theta dependence. That is one advantage. So you have to do now only one integration, right? So d theta comes as a 2 pi, and you have to do r dr e to the minus alpha r square by 2. Very simple, this integration you can do. To define u equal to alpha r square by 2, so that r dr is du. Okay, alpha will be there. Alpha r dr will be equal to du. So I square alpha will be 2 pi by alpha du e to the minus y, this. And then alpha, I alpha will be just square root of this, because I have evaluated I alpha square. right? This is fine. Now suppose I take the derivative of this I alpha. If I take the derivative with respect to alpha, then one x square by 2 term will come. So what I will get here is that minus half times minus infinity to plus infinity x square e to the minus alpha x square by 2. And see, if I divide this by I alpha, then this is nothing but the average of x square, right? This is average of x square, right? If I divide this by I alpha is this, just the normalizations will act as a normalization. So this is nothing but the average value of x square. Now I have I alpha, right? So I can connect now the average value of this x square, right, with this I alpha, because this is d alpha is giving me x square average. I have I alpha always, I take the derivative, and this derivative is this, right? So what you do, you can very easily see by that x square is nothing but 1 by alpha. And what you can do again, you can take another derivative with respect to, alpha. What will come? It will come a x4. So you'll be able to calculate the average value of x4 without doing the whole integration, because this again you take the derivative twice, right? So that way you can go on doing this integration. So x square value you can calculate and get 1 by alpha. I hope this is understandable. Now you can go on doing this. What you will see, x4, x6, you go on doing this. What you will get, you can calculate the average value of x to the n, 2n. And you can see this will be 1 by alpha n. This 1 by alpha n is coming because of the dimensional reason, because if x square has a dimension, then you in the exponential you need to make the argument dimensionless. So multiply by a constant alpha, which has a dimension of inverse of x square. So that comes as a 1 by alpha to the n, right? And this you can go on doing this integration. You will see it is nothing but 2n minus 1, 2n minus 3 into ... 3 into 1. All the multiplication of all the odd number up to 2n minus 1. And this kind of thing I can write as a double factorial, 2n minus 1 double factorial, right? I can write like this, right? So you see, if I want to find out the average value of x to the 2n, it's nothing but 2n minus 1 double factorial, right? If alpha is equal to 1, then it is always 2n minus 1 factorial. Now, how do I understand this result? How do I understand this result? I can understand this result in the following way, because I have x to the 2n. So suppose I have 2n points, and I ask a question to myself: how many ways I can connect these 2n points in pairs? So I pick up 1 point, right? And then there will be remaining 2n minus 1 point. So this first point I can connect in 2n minus 1 ways, right? Once that is done, then I can pick up the second point, and that I can connect with the rest of the points as in 2n minus 3 ways. So next one I'll be able to connect in 2n minus 5 ways. So this particular integration is telling me that if I have 2n points, how many ways I can connect, those points in pairs. And you remember what I have done in the propagator, I have calculated the 2-point correlation functions, right? Suppose you ask me to calculate 4-point correlation functions or 8-point correlation functions, this result will be very useful. So this is the background. Tomorrow I will elaborate more, but this is what will help me to determine certain factors. Okay, so x to the 2n average for a Gaussian kind of distribution actually gives me the result of how many ways you can connect 2n points in pairs. So take an example, x to the 6. So this will be, I can write as x, right? And then 1 point I pick up, I can connect them in that point with any other 5. So 5 ways. Then 2 gone. So out of 4 I can pick up 1. Then that I can connect in 3 ways. So 3, and the rest 2 points I can only connect in 1 way. So 5 into 3 into 1 is 15, right? So the value of that x to the 6 average value will be, in your case, 15 by alpha cube. This pattern, that when I calculate the correlation functions, right, this pattern of correlation functions will lead to the is very similar to the Weeks theorem, or this is actually connected to the Weeks theorem, which I will start tomorrow. As you see, I have the intention to get the time order product, and I just told you in my scattering matrix, what is appearing actually is the time order product of the operators. So first thing, I should learn how to evaluate the time order operators, and this theorem will help me how to do that. So today I'll stop here. This is the right time, place actually to stop, and we'll see. We'll continue tomorrow. And if you have any question, let me know.
So any questions from the audience?
So was it very difficult that because nothing is understandable, or what? Is this course is very difficult? Let the student react.
Yeah. Let the students react. Yes.
No, sir. Until now, it has been not been that difficult. One by one.
Let us have some interaction. Otherwise, if it becomes a one-sided game, then it's not very fruitful.
So until now, it hasn't been that difficult. But I want to ask one question here. So, where will we head tomorrow with all these formulations that we have studied today?
Tomorrow I will discuss the Weeks theorem, and then I will try to introduce you to the slowly going towards the Feynman diagrams. But I don't know how much I will be able to cover, but we are going towards the Feynman the Feynman diagrams. But you should tell me that honestly speaking, this takes some effort from my side also. I don't mind for that, but it should be fruitful for you.
Any comment from the participants?
Is there any communication gap? You have any problem? Because if I go on telling and you have some problem, then it will not and lot of things have been discussed. So you should also try to go through those things. I don't know, you might have other assignment also, but otherwise it's it will be difficult. So what is the feelings of the audience? I need to know that honestly, because I personally want that it should be fruitful also. You learn something and then
Definitely,
okay.
Sir.
Yes.
Sir, I am okay.
Yes.
Please,
Okay. Yeah. Khan,
I am asking a very simple question. Actually, I want to just want to see that why they taking the higher order derivative. So we do d dx and then again d2 dx2. In case of this notations in the del covariant and contravariant, should we take both first order and second derivative as contravariant or covariant, or we have to mix them? This is one question from my side.
It will depend on the nature of your tensor. No, it could be a mixed tensor also. So it will depend on the tensor, but I have not yesterday discussed tensor. I have only discussed the vector. Okay, but for mixed tensor it will depend. Yes.
It's a partial derivative. I'm talking about the partial derivative. One with a del x, then del y. So, and in case some case there is some contravariant notation and covariant notation. So that depends on the tensor where our function we are discussing, right?
Right. It will depend on the nature
There is
of the
no
vector.
thumb rule for that. We have to always take one covariant and another contravariant. That is not the rule, I think. No?
Right. Yeah.
Okay, sir. Thank you for clarification.
And is there any other question? Today it was difficult?
No, sir. It was nice today. Actually, everything is going more interesting and quite understandable. We got that the derivative of the operator, as we have learned that the Ehrenfest theorem was there. The first derivative of the operator gives the Hamiltonian commutator of the Hamiltonian, and then express time dependence if they are then del or del t. So same thing we got here today in the in interaction picture. I think that we got the operator.
That is right. So thank you. But point is that I mean, as teachers, you have more experience. So what is your view? I mean, is it? What I'm saying. Let me just complete. That students may be more frank to you. So you please discuss with them and give me some feedback. That will be because there will be more you may be more approachable, though I mean I'm very much approachable.
But no, I keep myself silent. I want to listen from the students, but they are not yet. So.
Professor Alam, I think after getting the notes, if any students can ask after seeing that will be maybe useful.
Most welcome. I love interactions with the students. No problem.
Yeah. That may be useful for them also. Well, sure. Because in that case, the discussion may be from your previous lectures also.
Sure. I mean, it's all right. I mean, any point I can discuss, and for more elaborately, somebody wants, I can refer to some book or something. No problem.
Yeah. Of course.
But only one thing is that I'm saying, trying to ask is that whether it is becoming too difficult for you. I mean, you mean students. That's what I.
Yeah, of course.
Is it becoming too difficult? I want to know that part.
No, until now it hasn't become too difficult. It is understandable, and we are able to connect the dots so far.
Good.
For me, yeah.
So, okay, very good. So, and actually, let me tell you. Very frankly, that quantum field theory is a difficult subject. There is no doubt about that.
That is true.
So it's a difficult subject. So that is why I am not trying to jump anything. And if your concept is built correctly, this is interesting. And since this is the only theory for the microscopic world, for the microscopic universe, this is the only successful theory. So if you know quantum field theory very well, you will be able to work in particle physics, nuclear physics, condensed matter physics, whatever. I mean, that will be more difficulties because you can apply this to in almost all areas of physics. So because this is the only microscopic theory which is still now has no alternative. So this and it is difficult. I can tell you it is difficult. So that is why I am trying my best. But you should also tell me if there is any gap.
Yeah. Professor Alam, one request come from Dinesh Tarachandani that can you please go a little slower?
Oh, sure. I mean, that's what I'm saying. That is the input I want. So when I am fast, you don't hesitate to stop me. So I will be able to immediately change my pace, so no problem. Thank you. That input is helpful. But if somehow sometimes when I am becoming fast, stop me. I mean, unless it is helpful for you, there is no point, right?
Yeah, of course.
But today it was okay or not? I mean, today I was too fast, Dinesh. So tomorrow I'll little bit recapitulate then, because today what I discussed is extremely important because I am going towards the Feynman diagram, which is,
Yeah.
Okay. So tomorrow, as somebody said that I was a bit faster, tomorrow I'll recapitulate certain points. Okay.
Of course. And if possible, if you send the notes earlier, then they can see it, and after that you explain it. I think it will be better for them.
Okay, so let me try. What happens sometimes, you know, actually I'm not getting time. I have a plan to type everything and make
of course,
you know,
of course.
but that time I'm not getting. Not getting.
Of course.
That is one limitation. This needs some time because typing takes a lot of time. So it will be, I almost want to make like a lecture note kind of thing. But let me see. But anyway, so tomorrow's lecture, if possible, I will send you in the daytime so that you can distribute.
Okay, thank you very much. Oh, some request is there. Okay. Oh, okay. No.
So this comment.
You can see the chat, Professor Alam. You can see the chat box. Yeah.
Oh, somebody said that this speed was okay. So fine. Okay. So, but anyway, so I'll tomorrow, but still I'll be slower because I want that maximum, you know, participants, should be coming with me. So I'll be tomorrow a bit slower, and I'll recapitulate a few points which are very important because today I have introduced the Feynman propagator, which is a ingredient of the Feynman diagrams. And that contour integrations, I think you understood because you did it earlier, I guess.
Complex.
But I'll recapitulate a few things tomorrow. Don't worry.
Okay.
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 Okay. Thank you, sir.
Thank you.
Very classic talk.
Thank you.
So,
okay.
Do you want to say something? Okay.
Okay.
Okay. So good night.
Okay. Good night. We'll see you tomorrow. See you tomorrow. Okay. Good night.
Arnab, can you hear me? Arnab Dasgupta.
Yes, sir. Yes, sir.
What about how are you enjoying this lecture? It is okay, or you are facing some problem? You can share.
Yes, sir. I'm understanding, but I have missed some classes. So if I go through the notes, it will be better.
You got the notes?
Yeah. I've got it today. I will go through it today, and tomorrow I think it will be better. Sir, I haven't got the day 4 notes.
Day 4 is if not, we have also received. He will send us today, I think, tonight, and
okay, sir. Okay, sir. Okay,
and
sir.
And once
also,
I request all participants who are present here to put your actual name, a proper name, which will be seen in the certificate, written in the certificate, and your affiliation and designation, if any, so that the certificate will reflect the correct data about yourself. This is my request. So you may mail in the email address provided, lsift2020@gmail.com, or you may write that if you feel free. Then in the chat box we'll take it from there. So thank you, and again I request you to join tomorrow at the same time, 7:30, and to enjoy this lecture and put your valuable comment. As the speaker has many times, so he maybe feel better and may get some interest if you give feedback. Because
he always wants some feedback from the students. He always
much interested to give his the best to students, and that is very. We are grateful to him. We should be grateful to him that he is giving his valuable time to us and always encouraging us to learn something. And so I once request you to take the maximum you can get from him. So thank you once again. Good night, everyone.
Okay. Good night. See you tomorrow.
Okay, good night.